let's get started again. I'm going to try to dive fairly deep into what Lindsay was mentioning before with retention time, calibration, and prediction of what retention time a peptide is going to come out of your column. And what we found to be the most reliable way to do this at this point is to use something called IRT, which I think she explained briefly. And I'm going to dive into more detail, and we'll look at how it works in Skyline. And you should learn enough, certainly to use a standard that you purchase, but also even to calibrate based on endogenous peptides. So Lindsay said you can there are these standards, and there's a growing number of them. And it seems that anytime any company creates one, they contact us and try to get it into Skyline, and we really help. We're happy to put them in Skyline. So there's a growing list that we'll look at in a moment. We'll see how long it is. But then you can also just find endogenous peptides in your experiment, or if you're injecting stable isotope labeled standards, you can use those as well for your own peptides. They don't have to be one of these special IRT mixes. All right, so retention time alignment with this kind of linear regression has been going on for a long time. It gets used in a lot of software. Some software uses actual linear regression. Some software will use some sort of smooth line regression, like a low S regression. But basically, they're still just coming up with a function to take an X value and give it a Y value. So this is another part of Skyline where we're aligning DDA runs, and software like MaxQuant does this. It's very typical of anything that uses DDA data and extracts MS1 chromatograms to align between runs, so that because in DDA we don't get every MS1 peak doesn't get identified. We don't get an MS scan for every MS1 peak, and even if we do get an MS scan for every MS1 peak, it may not get identified by our peptide search software like Mascot or Sequest, right? So definitely in MS1 chromatogram extraction, in order to get peaks across a whole bunch of samples that match up, and we can do quantification across those samples, we really need to say, okay, I saw it in this one sample here. It's probably in the next sample very close to there. And the way people do that is they do a regression, and then they say, so this is, you can see S9-101, and this is aligned to, so this is the one ending with 47, and this is ending with 220. So 247, 220, it's a lot there. This is the alignment of them. And you can see that there's really incredibly good correlation between these two samples based on the identifications done by some search engine. And so you can actually see that their R is 0.99 or better usually. And so that means very, very good correlation, obviously. And then you'll see that the slope is really pretty close to 1. And then the intercept is varying from 5 to 2 or more, right? So that means that most of what's happening here is that there's a shift in the gradient. I mean, it's not, if this were closer to 1, it would be all shift. And if these were all just 1, then the only thing that would be happening was the gradient shifting earlier or later, right? Because the 1 sort of says, oh, things are, I guess what would higher than 1 would mean, one of them means things are coming out in general earlier and things are coming out in general later. But the intercept here, that's saying that 5.5 minutes later. So the 247 is coming out generally 5.5 minutes later than the 220. And we do this regression to know that. You can also see how many points we get to use, over 1,000 points here. And these are just the MS spectra that were identified by, in this case, UW sequest. It's a sequest search, and I think in yeast or something, and we're getting 1,000 peptides to align, and you can see the alignment's quite good. So then this is that data as I had first logically ordered it in Skyline. And so you can see this is S1. So it's a calibration curve, and these are the various concentrations, 1 through 13. So it's a 13-point calibration curve. And what do you think when you see this? Does this look like I probably have the same, or what do you see? Have you been looking at some of the data? Does this look similar to the data you've been looking at in Skyline for attention time? So what's the problem? What would you like to see? What do you expect to see? Yes, you'd like to see a straight line, yeah. And so is this just normal variance, do you think? So I had never seen anything like this. I've seen sort of like not necessarily straight across, but some sort of variance through retention time. I've never seen things jumping around like 3 minutes. And so that was weird to me. And so that's when I finally figured out what was going on, I implemented a feature so that you can right-click in this graph and order it by acquired time, and then you'll find out that actually this is the way it was acquired. So who can guess? So if this is a calibration curve, I'm going from 13 to 1. This is the way I'm acquiring it. What is my most intense concentration probably in this calibration curve? S1. And why is that? What? Yeah, right. Because of carryover and stuff, you generally run calibration curves with the lowest concentration first and then the highest concentration last. There were probably actually some wash runs in here or something. I bet they didn't just cycle right to S13 again, but they're acquiring it in 3 different cycles, right? So that's actually blocking, and that's the way you want to do things if you're doing so it's 3 different calibration curves. So, but what really happened to the chromatography? Like this is fine. I actually, anytime I see that basically the peaks are overlapping, I'm like, okay, that's kind of what I expect from chromatography. But you can see that we drift from sort of eluting later for a while. Maybe the column wasn't fully conditioned, and you'll see more movement in the chromatography if you just start with an unconditioned column, and then eventually it kind of drops off and levels off again. So there's change in the chromatography. We'd prefer to see it go straight across, but this is not, it's not the variance that we thought of here. And then now if we run an alignment, so we use all those regressions and those linear equations to translate between, this is just translating everything to one certain replicate. It's S11306, just arbitrarily chosen replicate. But if we do that translation, right, so we have an equation, we did a regression, we have a linear equation like that, y equals mx plus b. We just take every x here and plug it into the linear equation, and now all of a sudden, you just cannot see that change. Like, I mean, it's not perfect, but everything is now, the centers are within, half a minute of each other in general, and you can't see it. You can't see the curve that we were seeing before. And so now our goal is to do the same thing in a targeted experiment where we may not have thousands of things. So we want to be able to do that kind of alignment. And the answer to that is this IRT concept. So one of the first ways that this got practiced, and certainly the way it's reported in this Escher Proteomics 2012 paper, is to have peptide standards. So these are 11 peptides. You just inject the standard into your sample, and then you can be very confident that you're going to get, these things are mostly up in the hundreds of thousands of ions per second, and they come out very nicely, and they're very stable in retention time, and they span some amount of the gradient. Turns out they span less of the gradient than we'd hope, but they do span some of the gradient. And then for the paper, I encourage them to do this experiment where we switch gradients to prove that we could get a reasonable prediction of retention time, starting with, I guess this is like a 45-minute gradient, which then gives you a clue of how much of the gradient we span. We span about 2/3 of the gradient. In hindsight, I've seen data where I really wished we got a lot closer to 40. And then this is a 90-minute gradient. And so you can see that there's still, everything's coming out in the same order, coming out basically the same relative distance from each other. Like if you go, oh, that's kind of a big gap. Oh yeah, that's kind of a big gap. Ooh, that's a really close gap. Oh, that's a really close gap. So you can see that the relative distance of the peptides is not changing, and they're still consistent, and that's the basic principle. And now if we put a whole bunch of other peptides in here, they would generally elute fairly consistently, and they would elute fairly consistently relative to these landmarks. So if we inject standards, we get these landmark peptides. We could also choose landmark peptides just from our samples. So the next thing is, whoa. So these are the standards. This is potentially a retention time alignment from sample A to B. So this is actually, so this is these two, right? These two samples, one with a 45-minute gradient, one with a 90-minute gradient, and when we do the alignment of each other, we get an R of 0.999, and we get this equation with actually a shift of 0.55 minutes, and then a slope representative of the fact that we've compressed the time from spanning 10 to 30 to 15 to 60-ish, 65. So if you're not just going to buy a standard and inject it, this is what you need to have a good set of peptides that you can do this kind of alignment on. You want 10 to 20 peptides at least, and they need to be consistently measurable in the sample. If they're coming and going, and you can't measure 20 samples and get every peptide every time, then maybe they're not a good choice. And then you want them to span the gradient of interest as much as possible. Remember, like the peptides are not just going to elute totally linearly, and so the more if you only span a portion of the gradient, you're making a linear approximation, and if your gradient actually curves a little bit, so this is what I've seen with the diagnosis ones that span 2/3 of the gradient. If the end of the gradient starts curving a little bit, it can get pretty far off. Whereas if we had a point out there, then at least the line would go through the middle. So here are several of the available. There's these three that Lindsay highlighted as well: diagnosis, Pierce, Sigma Aldrich, and then just your own heavy reference peptides. And we also use we use a heavy label ApoA1. That's from Sigma Aldrich, but you could also use analyte peptides. So what we want to do, the first thing we want to do for IRT is to get a calibrated value that's retention time independent, right? So this is a little bit like we're all used to dealing with masses and Daltons. Well, somebody just chose, carbon is going to be 12, and then everything else is relative to carbon 12. So this is essentially, you have to make a choice. And in this case, diagnosis, they defined a certain IRT scale, and they just chose that one of their second eluting peptide was going to be 0, and their last eluting peptide was going to be 100. And that's just as arbitrary as C12. That's 12 Daltons for carbon 12, totally arbitrary. But those are the anchor points that everything else is defined for in a certain scale that we named IRT C18 because we had defined it in a C18 gradient. So then if you think about it, it's like, okay, you choose any 2 points, any 2 of your peptides. And Skyline now, we're going to go through this. Skyline allows you to do this. Choose any of your 2 peptides and give them 2 arbitrary values, like 0 and 100. That gives you an equation, right? It's a line, 2 points, define a line. You can have an equation that maps from X to Y. And so now X is your measured time, and Y is the calibrated space you're trying to map into. And now I can take the measured times of all these other ones and put them on this line. I can give them scores with that equation. And so that's this, right? So here you go. This is I just calibrated the scores for all of the diagnosis IRT peptides based on that equation. And Skyline does this all automatically. You can work this all out in Excel or using R or something, but Skyline has some nice tools for doing this. And then once you've done that, then you have an IRT scale. You have a set of peptides, and you have their values in this new space. And that allows you then to go out and measure a whole bunch of other peptides with your peptides of interest. You can see stars on all the IRT peptides. And then when you bring them into Skyline, it'll look like that. Skyline will go, oh, yep, I know the IRT values for these ones. And here are the measured times, and there's a regression. I have no idea what the IRTs are for these ones, so I just plot them out here. I know what their measured times are, but I don't have a score for them yet. And so then you do some more steps in Skyline, and your goal is to actually get them on this line. And that actually you have to do this way, because in this graph, I'm showing the measured times as Y. But what I really want is I want the measured time to be my independent variable that gives me a score. So we flip things around here. You do a regression of these points to get a linear equation where X is the measured time and Y is the score. And then you just plug in every measured time as X and get a Y, and now you have an IRT value. So again, it's just right back to that. We did a regret. We measured the IRTs, and we also measured a whole bunch of other things with them. We did a regression to get a linear equation with the independent value measured time, and now we can give everything else a value. And we're going to do this all in Skyline, but that's the principle. We're just applying this equation, and then we get this. And so now here's a new data set. And now I want a new data set where I've calibrated everything. So I've got their scores, right? That came from my last experiment. I gave everything a score. And now what's more interesting to me is going the other way. I've got a new instrument, new column, and I just set out the gradient. I want to know how to measure these things, maybe how to schedule for SRM or how to extract them from DIA or what have you. I've got a library of scores. How do I get to measured times? Well, it's pretty simple. Again, I measure my IRT peptides. I do a linear regression on those. Oops. Yeah, so these are the steps. I'm going up, sorry. So that's what I'm trying to do. Oh, no, okay. So, so anyway, so I measured these. That will give me this equation. And then I can take these scores as X values and predict into the retention time space. because, right, this is measured on my new column. I can now predict where all these other peptides are going to fall in the measured time space. That's what that looks like. These are all now predictions, or maybe they're measurements. And then these are the same set of peptides predicted by just the sequence-specific retention time calculator, SSR calc. So it's way better to have an empirical measurement of something based on these landmark peptides than to just use the properties of amino acids to predict where a peptides are going to come out, especially if you have modifications. So if you're dealing with phosphorylations or all kinds of modifications that can cause shifts in time, the sequence-specific retention, the SSR calc can only predict raw peptide sequences. It can't deal with modifications at all. Okay, so let's actually try this in practice. That's the basic theory behind it, and now we're gonna go ahead and try it in Skyline, see the tools that Skyline provides for this. So close this down. So you want to go to your flash drive. Everybody have their flash drive? Plug it in, and then in data tutorials, there is an IRT folder. So data, tutorials, IRT, and then I usually just have everybody copy their data into documents. So I just grab this IRT folder and drag it to documents and drop it on the documents folder so that you get a subdirectory. It should copy pretty fast. There's not that much data in here. Let's have a quick look at what is in here. So we've got 4 data files, an IRT definition, a file called IRT human, and a file called IRT C18 standard. So I guess let's just double click on IRT C18 standard. So these are the, I guess you can go edit, expand all precursors, and you can have a look at the peptides and their transitions. So the diagnosis group chose 3 transitions per peptide, and a precursor for every peptide. Are they all charged 2? Yeah, they're all charged 2. So they chose the charge 2 precursor for every peptide and 3 transitions for it. And this is what we would measure in that standard. If we were trying to do our own, we were trying to build our own library, how would we do that? We were trying to come up with our own peptides that we thought might be candidates for this. How would we do that? We'd probably start with more than we need, and we would try measuring them in some number of replicates, maybe 10, because we're looking for things that are really consistent, and then we would pare things down based on what we found in those 10 runs. We would try for things that are very stable. But anyway, Biognosis did all the work for us. They've chosen these peptides and these transitions, and we're now going to look at data. You can pretend that we're going to start out pretending that we're calibrating our own IRT standards. So maybe pretend you've already run a bunch of things, and these are the 11 peptides that you've come up with that you think are great landmark peptides for your samples. So you're planning on doing maybe thousands of runs of a clinical sample, and these are going to be your standard peptides. Or if if these really truly were just injected biognosis peptides, I'm going to show you a bit later how quickly you could get set up for that. But we're going to start with just pretending you're defining your own standard. Okay? So you get to choose the C12 and set the calibration. So the first thing we're going to do is go File, Import, Results. So we've chosen our standards. We're going to import some results. We're just going to treat them as single injection replicates and click OK. And what we're going to do is we're going to import these first two 30-minute, I think it's actually a 45-minute gradient, but it says 30-minute here. So this is the 30-minute gradient, apparently. Just two of them. And we'll open them as if they were replicates. So does everybody have that? Yeah, so it'll be in your IRT directory. Mine's under my documents, and you just choose those. You can do that by pressing the control key and clicking both of them. Does everybody have those? 30-minute. And then click open. And Skyline tells you, well, they've got a common prefix and a common suffix. So do I just want to name them 1 and 2? So generally the Skyline graphs, a lot of the replicate graphs don't look very good with really long names. So we try to compress out common names, and in this case, yeah, that's fine. So we'll just use 1 and 2. So click OK, and Skyline will start importing them. On my machine, it's hiding the. So I just opened the import graph. So do people know how to do that? If this import graph can be hidden and shown just by clicking on this button down here in the status bar, so that the status is tracked down here as well as up in this thing. Anybody else done? Okay, so who had less than 30 seconds? Yeah, how fast? It just finished 30 seconds? Did anybody else have theirs pinned so that they can see? Mine's there's a little timer here. I don't know. Maybe you have to, in order to see that, you have to push this push pin down, and then it will stay up. But anyway, so one thing you can see here, you can see all of these are the IRT landmark peptides here, colored ones, and then the gray tells us, well, this is SRM data. Well, there were a bunch of other things measured too. We'll come back to those later, but right now we're just pretending that all we measured in these ones was the IRT peptides, even though we did measure other things. So I'm going to close this. I'll take my peak areas and move them over here. Do people know how to dock windows pretty well at this point? Yes? No? Yes? You can grab the title bar of any window and it kind of floats around, and then where it gets docked depends on where your cursor is. So where that arrow cursor is, you have to position it inside one of these boxes. And then you'll see as soon as your cursor gets inside one of the boxes, Skyline will, snap the blue rectangle to show you where it's going to put the window. So I'm just going to put it over on the right side here. And then I'm going to do the same thing with retention times. And so you can see the peak areas are relatively stable between replicate 1 and replicate 2. You can also, in retention times, do people have both their windows docked like that? Okay, so yeah, so you could have things as tabs, or you have these with the title bar. And so if they're showing up as tabs, that means that they're sort of part of this space with your chromatograms. So they might be sitting here like this, and they have tabs versus title bars. The title bars you get if you go all the way to the edge and dock them on the edge. And then, yeah, and then you could take you could separate these two like this, so you can kind of see them one on top of the other to get a sense of where the peptides are eluting. And then over in retention time plot, we can right click and change the value to just the retention time. So right now it's showing a bunch of different values potentially, but if we tell it to just show retention time, then we can get a sense of how consistent the retention times are. And they look pretty good. They look better than the peak areas, right? The peak areas are kind of crossing over each other, whereas these retention times are going straight across, which is what we'd like to see. We could maybe zoom in a little bit to see, in a single one. Okay, so when we zoom in, you can see that there is actually some slope. So which run is eluting earlier? Yeah, the second one. So we're seeing some downward slope between 1 and 2. Right? Okay. So if we did alignment on these, we would expect to have an equation between the two that had the second run coming out a little bit earlier, maybe just a few seconds earlier. Okay, but now let's go and do what we would do so we've got some runs. We know where these things appear in measured time. Now let's give them IRT values. So we're just going to assign an arbitrary scale. And that's going to be the start of our IRTs. So we'll go to peptide settings. And then choose prediction. And you can see we don't have a retention time predictor, but before we can have a retention time predictor, we need a retention time calculator, which is this button over here allows us to deal with a retention time calculator. So get to peptide settings, prediction. Is anybody behind? Anybody need more time? Okay, so click on retention time calculator and add. So we start with something empty and we'll call it IRT, or actually we'll call it diagnosis IRT-C18. And now we have to create a new database for this. So click create. And you should still be in your IRT directory where you started, and you can just call it diagnosis C18. Okay. Or whatever, or B18, or whatever you want, really. It doesn't matter. Call it what you want, and then save it, and that will just create an empty IRT database, which you can see has the extension .irtdb. And then drop this list here. You can see that there's, Skyline offers you just a set of options, including diagnosis, just 10 of them, 11 of them. That's the full set of diagnosis. So we have 2 diagnosis things. The 10 just gets rid of the one that's lower than 0. And then we have Pierce, Replical, which I think comes from Waters, and SciX has one, and Sigma. And then the ApoA1 that I talked about, that's also, I think, from Sigma. And then CIRT, there's a whole paper on that one. Then that's just a set of highly conserved peptides in eukaryotes. So they may be a good place to start if you're looking for endogenous peptides in cell lysates or something. But we're not going to do that. We're not going to use a stock one. We're going to calibrate our own based on our own measurements. So you have, at this point, we're still pretending that these 11 peptides are endogenous peptides that we've picked for ourselves and just measured. So click calibrate. Yep. Oh, I created one and I named it Diagnosis C18. So I click create, and then I just named it Diagnosis-C18, and then save. And that's just an empty thing. It's not at all useful to me until I do some work. So let's calibrate it. So click calibrate. And here we start with IRT value 0 and 100, and you can make those, 100 and 1,000. Don't do this because I'm not going to have you do this, but that's completely arbitrary. This is the C12 part of things. So, but we're going to leave them at 0 to 100. We're going to click use results, and Skyline then will go get the measured times of all of the peptides in the document. And it will assume that you want your fixed points as the last, as the first and last peptide, first and last eluting peptide. You can see the times go from 11.3 to 3.4. But then, like diagnosis, we're going to say, no, we actually want to use the second to last eluting point. So this GAG set, the GAG set peptide is going to be, so all we're saying here is, this is what I showed you in the slides, all we're saying is that this gets the IRT value 0, and the other one gets the IRT value 100. Those 2 points define a line, and I can convert everything else to give them IRT values based on that. So that's all I need to do here. Why did they have diagnosis 10 and diagnosis 11 and get rid of the first one, or why did they use the first? Why did they not? Why didn't we just have it checked like this? Because they did. I have no idea why they did that. It's kind of problematic and not that. I mean, one of the nice things or one of the not so nice things is it makes it hard to calculate CVs of retention time, of IRT values. But anyway, so what? Yeah. At this point, there's no. At this point, there's no linear regression. We're just trying to define. We're just trying to define the distance, and then everything else is going to get calibrated from that. So let's just I don't know why they didn't do this. I would have preferred they didn't use 0. I would have preferred they did 10 to 100, so that that most or all, it would be great if they defined a range where very few peptides would ever get 0, because it's kind of problematic that that retention time gets expressed in zeros and negative values and stuff like that. So, but this is what they defined, and now because they defined it this way, it's a useful scale like Dalton's, and so we actually try to define all of the other standards in this scale too. So, but anyway, so let's go ahead and redo this, what they did. Click OK, and you can see that now Skyline has assigned the GAGS peptide 0 and the last peptide 100, and everything else somewhere in between that, or actually the LGG peptide less than that, right? It's negative. So let's go ahead and let's copy all of that by clicking on LGG and then just dragging until you have everything selected, and then Control-C to copy. And now what we'll do is go back to this folder, the Documents IRT, and open up the IRT definition. So this is a canonical definition that appeared in the paper and that you can still get off the Diagnosis website if you go there. And what we'll do is, so if you selected all the cells that as Skyline defined them based on the measured data, now we can go and say Control V, and I'm going to turn off wrap text, and you can see that the peptide sequences match exactly. And then you could have a look at how close. I'm actually even going to delete these intervening columns by doing Control minus, and you can see how close we got. They're not the exact same values, which tells us that Biognosis didn't calibrate their values off the data set I'm using. But they're pretty close, right? So that's it. That's what Biognosis essentially did. That's what you could do to calibrate new values. So let's go ahead and close. And don't save that. Yeah. If your numbers were, are you saying that that's what you're actually seeing, or no? Well, you have some options. I mean, you could, they should come reasonably close, but you could also just say, well, you could soldier forward, and I have seen large data sets where it turns out to be better to recalibrate the IRT values on your chromatography than to use the canonical values, because there will be some variance. And yeah, so Skyline now will automatically ask you, if you do a really large data set for DIA or something like that, and you say, I'm using IRT C18, it will say, hey, do you want to use the Biognosis standard values, or do you want to recalibrate? Recalibrating turns out in many cases to be a little bit more accurate, because there is variance, and I've seen libraries that came from Biognosis that then got run on some other chromatography, and when you look at the retention time correlation between the IRTs in the library and the measured times, there's like this curvature, and so not all gradients are equal, and so yeah, you're gonna lose some precision taking IRTs measured on a completely different system and applying them on a new system. It's still pretty good. It still tends to be better than just trying to predict it based on the SSR calc. But it's definitely better to have calibrations of peptides on your own system that you then use on your own system. But anyway, so yeah, if you tried this exercise and you were really far off, I don't know, post to the Skyline support board and we'll help try to figure out what's going on, because they should generally be pretty close. Okay, so so the other option we have is just to go ahead and choose Biognosis 11. And it will say the list of standard peptides must contain only recognized IRT C18 standards to switch to the predefined set of IRT standards. What? The list of standard peptides. I guess what I have to do is select all these rows and delete them. And then I can choose this set. So these are the canonical values that we're not going to use the ones that we just calibrated. We're going to use the canonical values, or who wants to use the calibrated? Who wants to use the canonical? Nobody has a preference. Okay, well, we'll just keep going this way. Okay, so click OK. And you can see that Skyline automatically creates a retention time predictor for us, and we can click on the drop down and say edit current to see what it did. So you can see it said Biognosis IRT C18, and it gave us a window of 10. And so that means if we went out and now measured some, if we went out and create a scheduled method, we would have a 10-minute window around everything. I'm going to quickly just check what is the, so this is the tutorial that we've sort of been going through. It doesn't quite say what we choose. There we go. 5 minutes. So we're going to switch to a 5-minute window here. Yeah, that it's going to tell the instrument to collect data for. So in SRM, we have to tell the instrument ahead of time how to schedule the acquisition. And so, yes, this is a 5-minute saying, I want a 5-minute window as the period where I'm going to try to capture my peptide. So click OK, and then click OK again. And then let's go ahead and save as. Don't save right back to the same thing. And we'll call this dash. So IRT C18 standard dash calibrated. And save that. Okay, so and let's go ahead and switch retention times right now. So if you right click on retention times, we can choose the graph regression, and then we have to do score to run. So it's also up on the view menu, view, retention times, regression, score to run. And then I'm going to pull this off so that I can make it bigger and you can all see it. So here you go. These are the IRT peptides. And so you're seeing the scores that we've given them against the measured time. And why are things not perfectly on the line? We would if we just calibrated. So we use the diagnosis one. So hang on, just everybody hang tight for a second. Peptides. If I went back to this calibrator, this calculator, I mean, and I deleted everything and calibrated it the way we were going to do, then here's the calibrated ones. And now I believe if I go OK and OK, everything is really on the line. I don't know why that's showing up there, but yeah, things are on the line. If I actually, I guess I can also choose to plot residuals. Whoa. Okay, I don't know what's going on there. So let's go back. I'm getting too far afield. Plot correlation. So I'm going to go back. Hopefully nobody else did that. But you can see how all the points are really on the line because I calibrated them onto the line. Whereas if I switch to the diagnosis 11, then I'm using the diagnosis canonical values. And when I'm done, then now things are not on the line. And now if I actually plot residuals, they look even much worse. Right, so this is sort of showing me how far away from the prediction line everything is, and there are some things that are half a minute off the line. When we look at them in that linear mode, they look really close, but and they are really close, but they're not super close. They're not on the line, which they would be if I had calibrated them myself. Okay, so let's plot back to correlation. Looks really good in this, and in fact, we have an R of 0.9991 with these things. All right, so let's go. So now let's go pretend that we wanted to, if you pulled this out like I did, which maybe nobody did, you can just put it back by double clicking and then it will pop into its position on dock to the window. Okay, so yeah, that's still all with the calibrated document. So I'm going to save that again. And now what I'm going to do is go File, Open. And I'm going to choose IRT Human. And edit, collapse all peptides. And so you can see that here are a bunch of peptides with no IRTs that I would like to calibrate. There's 124 of them. Or no, there are 124 proteins. How many peptides? 148. Okay, so that's what we would like to calibrate. And we're going to do that by first save this file as something new. File, save as IRT human-calibrate. Do I want to do that yet? All right, well, we're good. We'll do that. All right, so let's now import the IRT standards. So we're going to do that by just keep the selection on the top protein, and you can go File, Import, Document. So we're going to import another document into this document. And now we can do this IRT standard. So that's the original IRT standard document, which just has the standard peptides. Everybody got that? And open. So now we have all the standard peptides at the top of the document. And we're going to go change the settings, peptide settings. And we're going to choose our new IRT C18 standard, or no, whoops. This is, I've got extra ones here. Everybody else has Biognosis IRT C18. So choose that retention time predictor, the one that you just created. That's going to be your retention time predictor. And click OK. And you can see once you do that, if you've done everything right, you should get little clock faces next to the peptide icon in the targets view. Right here, you can see those little teeny circles with hands in them. They're supposed to be clocks. So if you don't see those, then something's wrong. All right, so yeah. I think you can leave it there. That's one of the reasons why I put the IRTs at the top. If you didn't have the IRTs at the top, then things might get a little weird. But if you put your IRTs peptides at the top, it should still work okay. Yeah. What I mean, there's only one measurement of it, right? It's gonna appear a measurement in the same place, and so sometimes sometimes people mix in measurements of if you're using endogenous peptides, you might have measurements of them down here because you want to actually have them included in quantification. Whereas if you just have them in the IRT standards, they're mostly just going to get excluded from quantification. So it's not something I love to see, but so ideally it's way better if you can have just disjoint sets. Makes things simpler. Okay, so now I just have to figure out which one did they actually measure. They measured. So we're gonna remove the heavy type. So you can see that these are paired heavy light standards with Scylla labeling. If you hover over one of the peptides, you can see like arginine plus 10. Heavy is arginine plus 10. So you can see that this document has heavy light standards, but when we're just trying to measure retention times, that's going to be too expensive for us to measure because that will cause us to have to measure, in this case, 4 transitions, 8 transitions per peptide, and we're really just trying to get retention times, and we're going to try to do it in as few methods as possible so that we use as little instrument time as possible. And so that means getting rid of some of these transitions. So let's go to edit. Actually, before we do this, let's just quickly save this as something. File save as, we'll call this human, I guess, calibrate 30. So go ahead and save that as calibrate 30. All right, so then we go to edit, refine, advanced, and all we have to do is we're going to tell it to remove the label type heavy. So this is just going to go through the document, remove the label type heavy, and click OK. All right, so now what did that do? So how many transitions did we have before? Anybody know? What? Yeah. So and I don't remember the number, so I can click undo, and then 1,231, and then I redo, and now I've got 632. So I'm obviously going to have a better time measuring 632. Can I do scheduled acquisition? Can I do scheduled acquisition? What do I need to do scheduled acquisition for these 600 transitions? I need predicted retention times, and I have no idea how to predict the retention times of these things. So I'm not going to do scheduled acquisition. I'm just going to acquire them. So let's go. We'll save this document now, and then we're going to export the transition list. And sure, let's say I'm going to export for a thermo transition list. If you choose multiple methods here, some of you may have single methods showing, choose multiple methods and then check ignore proteins. And then who has an idea of how many transitions you would like to acquire at any time? Who has a triple quadrupole? Okay, so how many transitions would you like to have acquired in any cycle for your triple quadrupole? Throw out a number. 200? Okay, so let's type 200. So how many methods would it take to what kind of triple quad do you have? You have what? Oh, okay, keep track. All right. Oh, yeah, sure, right. So, okay, so, and that is, what is it, like a 6,500 or is it, yeah, okay. So 200, and if we did 200, that apparently would take us 4 different methods to collect data on all these peptides. So Skyline will tell us right away how many methods But okay, so we don't need to be quantitative. All we need is just one spike that tells us where the thing is, right? So we're going to go even a little. We're going to push it even a little bit higher than here. That might be if you actually wanted to do a real quantitative assay. So let's say, what if we pushed it up to 400? Well, then we have two methods. But does anybody know what the, well, we can just sort of play with that. Let's say, what if we did 350? Two methods still. 320, three methods. So 340, two methods. 330, three methods. So about 340. So we can choose 340 transitions. We're going to get two methods. And it's just going to be full gradient. This standard method means unscheduled. So we can choose a method type standard or schedule. We're going to come back to schedule later. But right now we're going to do 320 transitions per method. 340 transition per method. Yep. 340. Yeah. 340. And you can see it says methods 2. And now we're ready. We're just going to export the method. So, or the transition list. So click OK. And go to your IRT folder. And we're just going to call this IRT-human and click save. And now if we go back to that folder, we should have two IRT human CSV files, which we could go plug into a thermo mass spectrometer, because that's what we chose in the list. Yep. So what we got here is we got this A is the Q1, so that's the precursor MZ, and then the Q3, which is the product MZ, and then this is the collision energy, which Skyline just predicts based on the precursor MZ, and then, as Sue was explaining, and then here are these are the peptides, the modified peptides. You can see the cysteines have a 57 plus 57 on them. And then these these four columns are not actually even used. Maybe the protein is, but these last three definitely are not used. But anyway, so that's the method, and you can just import that into a thermo method and then go collect it. And so now we're going to pretend that we collected that data, right? So if I now go into here and I go File, Import Results, then what kind of results are these? Are they single injection replicates? They're multiple injection replicates, because we had two injections to get one replicate. So we're just going to go one new replicate. Hey, we've got two data files. We're going to have two data files. We're going to import it as if it's just one measurement of the document. And Skyline's just going to fold them together. And we'll call this unscheduled. So that's the name of our replicate. Add one new replicate, call that unscheduled. And we're going to use two files. Click OK. And now we're just going to choose these 30-minute files again, because they are the two measurements of all the peptides. And then click open. And hopefully they'll come in about 30 seconds again. You can see there's no gray anymore. We're getting color for everything. And I've got my push pin pushed, so wow, that came in 14 seconds. Other people have their data imported. So I'm going to close this. And you can see that I've got the IRT protein selected, you can see that it was measured twice. So you have to measure the IRTs in every injection. And Skyline just did that automatically for us. I forgot to show you that. Documents, IRT. If you look at these CSVs, then you'll see that at the bottom, they both have all the IRTs, right? They all have the IRT transitions. So those have to be measured twice. You can see the chromatograms for those by choosing the file from this little dropdown on unscheduled. And you can also go to view retention times, replicate comparison, and you'll see both replicates. And this is the view we were looking at before. And you can see that it's labeled unscheduled 1 and unscheduled 2. But if you click on anything else, then you can see that those are only measured once. So the only thing that gets measured twice is the IRTs. Let's also now bring the view, retention times, regression, score to run graph up. Whoa, okay. Did everybody get that? Does everybody have a view like this? Look, they're showing? View, retention times, regression, score to run. And mine is in auto select mode, and so it's going to say the best regression I can get is using SSR calc. So you can see that the x-axis is SSR calc 3.0 100 angstroms. Do people have that? No? What do you have? View, retention times, regression, score to run. So this is just showing you a correlation plot between SSR calc and the measured times. And it's kind of okay, but not great, right? Everybody here? Need more time? Okay, so then we can now tell Skyline, well, I really want to see it with my new calculator. So right-click in this graph, go to calculator, and so you can see the calculator's check says auto. So Skyline's just choosing the one with the best regression. But if we tell it, I want diagnosis IRT C18, then it will show us this one. So why is the regression not as good in this one? Some of the regression looks really good, right? Yeah, that we don't have any values for a lot of these things. So Skyline's just kind of kicking out this minus 75 value or something for all these things. And they're kind of over here. So what we want to do is take these uncalibrated values and give them values, right? We know where they're measured. We know where they come out relative to the IRTs. Let me just put this back. So one thing I can do is, so if I click on a protein, it will show me chromatograms for every peptide in that protein, but it also works anything I select. So if I go Control A, that will select everything, and that will then show me everything sort of relative to my IRTs. So you can see a whole bunch. So now we know where our IRTs came out, and we know where every other peptide came out relative to the IRTs. So Control A to get this graph, and then I was just using my mouse wheel to zoom in. And you can see that not all of these are IRT peptides, only some of them are. But we know where they all come out relative to the IRT peptides. So what we want to do is encode that into our IRT library, right? So go to Settings, peptide settings. And we're going to click on the calculator again and say edit current. People have that? Edit current. So that brings us into this where we have our calibrated standards, but we have nothing else in our library. And really, the whole point of having a library is to have things other than the calibrated standards. So now we can click on add and say add results. And then Skyline will tell us, hey, you had 2 files. I found all 11 of your standards in them. And I'm giving you this slope and intercept with an R of 0.999, a success. If I click on one of these success things, I can actually see each regression separately. So this can be super useful if you get a failure. Basically should make us feel really great. It says 2 runs were successfully converted. Hey, we got 148 new peptides to add to your IRT database. And if we click OK, then it says, do you want to recalibrate? So this is the recalibrate thing. It says, hey, maybe you would do even better if we recalibrated the standard values to the ones that you measured. And we're going to say, no, we don't want to do that. But if you're doing a really big like DIA run, it's maybe something to consider. So no, we're going to leave the IRT values the way they were, but we do get 148 new values down here. And you can see that they're listed as 148 peptides over here. Is everybody good? Oh, you got lost in the calculator. Okay, I'm going to cancel. And so you got to go, so settings, peptide settings. And then you click on the calculator button and edit current. And then the last thing to do is just to say add results. So are you here? You with me? Click add results. It'll show you that it did a good job. Then it says, hey, do you want to recalibrate? And you just say no. And then you're done. So, and then we can now click OK on that. And you can see that as soon as we do, now you look over here at this retention time plot, and the correlation is awesome. So click OK again. And now we can even see, so the correlation looks good. Let's go ahead and check it with plotting residuals. Oh. What happened? Why are my residuals not coming in? What? Huh. Okay. What's it undoing? Change settings. Okay. Interesting. Whoa. But I don't really understand what it's undoing. Okay. Huh. I don't know what's up with that. But anyway, so, okay, we'll do undo for a second. And you can see the residuals aren't perfect. They're set, they're actually frequently, and this must have to do with some sort of rounding error. They're less than 1/10 of a minute away from the line. So anyway, I think I'm just going to redo just to be safe. I don't quite know. And then I'm going to put the regression, I'm going to switch the regression plot back to correlation. Yeah, what is that? It's got, okay. Yeah, it's having problems with auto-calculating its predictor. I don't quite know what's up with that. I guess undo. Did that fix it? No, I don't know. All right. So Now we want to go and do a run on a 90-minute gradient. And we want to measure, and we're going to want to measure everything eventually. But the first thing we're going to do is just measure our standards on the 90-minute gradient. So we've got this fully calibrated calculator. You can go ahead and save that. And the next thing we want to do is now go back and let me just check this. We would export a method. So we might go file open to this standard Skyline file, and we would export a method for this standard Skyline file. So we would just go file, export, transition list, and again it would be an unscheduled method. We just have a single one of them, and we would export that, and then go measure it on our 90-minute gradient. Okay, and then we would import that into our full method. So go back to IRT human calibrate. Oh wow, IRT 18 calibrate doesn't even have our internal standards. So what? Yeah, but it also has our data. I guess we could get rid of it. Okay, so sure. So bring up the calibrate 30, and we'll do save that as something else. Save as we'll just call this IRT human 90 and save. Okay, and now what we're going to do is we'll do edit, manage results, and we're going to remove all our results. Okay, and then now we need to add back our heavy standards. So edit, refine, advanced. Hope this works. Heavy, add. And okay. Yeah, so that's nice. It used to be that we actually added the heavies to the standards too, which is kind of a pain, but I fixed that. So, so now we're all set with a document that we would like to schedule this data, but we need to know where everything falls in the 90-minute gradient, right? Because now we have 1,200 transitions. That would take us at least 4 methods to measure. So we wanna get a new place. We want to know where these things are going to show up in our 90-minute gradient. So the way we're going to do that is just everybody click save to save this document you have. Does everybody have the heavies too? Did that go too fast through that? It's edit, refine, advanced, click add, and then add the heavies. So okay, so then we're going to go file, import, results, and it's going to be a single injection replicate because all we measured were the IRT peptides, and that's this first one. Even though the simple one is very, I want the simple, but no, it's I guess NS means no scheduling. So 90-minute without scheduling, and all we measured were the IRT standards. So click open on that. And you can see that, you can see our IRT peptides showing up. And there they are, close. And you see that nothing else got measured, only the IRTs got measured. But if I go to view, retention times, regression, score to run, here's my here are my measured things, and now it's showing me all the other peptides down here saying, hey, I don't have any measurements for these, but I do have IRT values. But you can see now and you can see that the measured times are from 10 to 65, so completely different gradient than we calibrated on, right? So what we want is predictions for all these others, and let's go have a look at the scheduling view. So go view retention time scheduling, and you get this. And I'm going to pull it out so it's kind of bigger here. And you can see that what it's telling me is that with a 5-minute window, if I can stand to have about 275 concurrent peptide measurements, and most of the time, so let's see, the maximum will be about, what is that, 260 something? Yeah, 265. But most of the time, I'm really more like 220 or under. So you know, it's believable that the mass spectrometer that we were talking about that could handle 200 might be able to get quantitative measurements of this stuff, right? So that gives us some idea. If we were willing to go with a 2-minute window, then we could get quite a bit less. And if we felt we needed a 10-minute window, then we'd have to go as high as 400 again. So, okay, so let's close the scheduling window. And file, export transition list. And you can see that it's saying 4 methods if you say 340, because we put the heavies in. But if I say scheduled, then now it says, oh, 340, I can do one method in that. And if I say 275, it still says one method. But if I said 250, then it takes 2 methods, right? So that kind of reaffirms what we just found with the scheduling view. Yes. Funky pyramid. Let's see. Okay. Okay. Yeah. We gotta knock off here in a second. So anyway, so you can see we could export the method. Now what we're going to do is we'll pretend we exported the method. We got one single scheduled method. We ran it on the mass spectrometer. Now we have data. Do people want to see that method? I mean, it just has retention time predictions in the transition list. So I think we're going to skip it since we're so low on time. So cancel, and we will again now edit, manage results, remove this one thing. So that was our calibration. That's how we came up with the predictions of our retention times. And then save that and file, import results. And now we can go collect the data that we collected with our one method. It's scheduled data, and so that's this simple raw. So file, import results, single injection replicates, simple raw, open. And you can see that we get our IRT peptides coming in, but we should be seeing some other peptides, although they're much smaller apparently. But you can see them coming in a little bit. And eventually, mine took about 20 seconds. And eventually, now I have a measurement of everything, right? If I scroll down here, the way I can tell that I have chromatograms for everything is I get little dots by them. And if I want to, again, I can do Control A to see the chromatograms for everything. And then, you know, here they all are. Other peptides in among my standards. And then this is just one single replicate measurement of everything. And if you click on the things, if you click on the other peptides, you'll see that they were only measured for 5 minutes. So this one goes from 5, well, that looks more like 6 minutes, doesn't it? 52 to 58. So I guess maybe this is diagnosis data. It looks more like they did 6-minute windows. But you can see that the mass spectrometer has only measured for a certain period of time, but we did get both the heavies and the lights. And you can also see where, Skyline is showing you where it predicted that this thing would show up. And you can see how close they were. And actually, if we go back again to our retention times regression score to run, then you can see this regression plot of our IRT values to the actual measurements. And you can see that there are a couple outliers. And that's just because Diagnosis and I disagreed where these guys would be. So they actually measured a range that didn't include what I measured in the tutorial, or what I chose in the tutorial. But for the most part, everything lines up really well. So that's a deep dive into IRT. It's an extremely useful concept if you feel like, yeah, I still didn't get it, which is not surprising. It's a pretty tough thing to really feel like you get. Once you get it, it's really very powerful. But we use it in SRM, PRM, DIA, not so much in DDA. But so yeah, it's worth understanding, and certainly you can save yourself some money on standards if you understand it really well. But there are standards that you can inject and save yourself some time. And yeah, there are a fair number of labs that I meet now that they just inject some kind of standard into every sample they ever process, that they have this way of normalizing the retention times. Yeah. It's the IRT tutorial. There's a webinar that goes with this. Yeah, you can probably find me, video teaching it too. I mean, a lot of this stuff is online. Hopefully this gives you a chance to interact, and you can certainly come ask me questions if you didn't get something. Yeah. So the yellow shaded area is our that's our 5-minute window. So we said we want a prediction. We want a 5-minute window. If you were to go and schedule this run again, based on these actual predictions, that's the window that Skyline would use. So yeah, so it can be really useful to sort of say, oh, if you set some sort of window, then you can have an idea of like, well, the peak, maybe we measured a bunch of stuff, but we don't really trust anything that's more than 2.5 minutes on either side of our prediction. So that just gives you an idea of some window. But yeah, and it would also, if we had done, if the diagnosis data had actually been collected based on my tutorial, then this would be the measurement window. You wouldn't see the chromatograms kind of sticking out to one side. Yeah, that's something we talked about even back in the very, it is possible. Actually, you can end up with different size windows. There's a number of ways of setting windows. There's even now an explicit retention time. So you can override, and people do this in small molecule a lot more, is they say, okay, with high flow small molecule, apparently the retention times are incredibly consistent, and people will just enter a bunch of retention times, and then you can do whatever size window you want, and you can override. Yeah, but there is no way. We originally, back in the day, we talked about maybe we could do it based on the width of the of the peak, so that something there are some peptides that just have you can't get around it. They have 1.5-minute wide peaks, and we'd rather give them 8-minute windows or something like that. And we just never did that. And that would require having some way of saying oh, the retention time window isn't a constant; it's a function of something. And we just never did that work. What? And what by what function of the measurement? What? But what is it based on? You mean running replicates and then looking at the distribution around some replicate? Yeah, there's not there. If you run one run, then yeah, the only thing that you could choose to make the window wider on is the width of the peak. Right. So that's what I'm saying. Then in the UI somewhere in Skyline, we have to have some sort of checkbox that says make this a function of the width of the peak, and then you have, so we just never implemented that because there hasn't been enough demand for it. It's been mentioned as like, hey, wouldn't this be cool? But nobody has sent us a data set. We're saying like, it's painful. I can't measure these peptides because of X. If you find that and you're like, I really need this function of the width of the peak thing. I mean, it could be also a function of the distribution, right? I ran 20 replicates in my data, and half of my peptides are rock solid in the same place, and half of them go all over the place. And so I want a wider window for the ones that go all over the place. Yeah, I mean, it's like those are just ideas that nobody has made tangible with a data set and said like, look, I just can't measure these peptides because of this, or boy, you would make my life a lot easier if you could do this. So the answer is no, it's not, hasn't been implemented. It's not because it hasn't crossed our mind and we haven't thought, hey, well, that would be kind of cool. It's just that it has never gotten high value enough to do.